Okay, welcome along. Little video on electric fields. Quite long, but let's crack straight on. So firstly, field strength is given by the equation E equals Q. Already restarted once, I'm not starting again. F divided by Q. It's force per unit charge on a small positive test charge, and we'll come back to the positive test charge a bit later. We've got two parallel plates, a distance d apart, with a voltage V between them for a uniform field. E equals V over D, so it has for units volts per meter or newtons per coulomb. Then we've got our radial field, so if we had a positive charge, our field lines would all be heading out like that, because a small positive test charge would be moved away, and the field strength is 1 over 4 pi epsilon naught Q over R squared, R being the distance from the centre of the charge. Oops, that was a disaster, wasn't it? From the centre of the charge out to our point here, and the other equation for the force between two charges, F is 1 over 4 pi epsilon naught. So epsilon naught is just a constant called the permittivity of free space. Look it up on the date sheet, 8.85 times 10 to the minus 12, Q1, Q2 over R squared, and the R is now the distance between the centres of the two charges, or their point charges between the two charges. And then we've got the energy consideration. So we have this special quantity potential. Potential is the amount of energy per unit charge on a small positive test charge. So potential energy over charge. And that's calculated by 1 over 4 pi epsilon naught Q over R. Remember, potential is a scalar quantity because it's energy, and energies always have no direction, whereas force and field strength both have direction, so they are vector quantities. I guess we should have a go at drawing some field lines. So if you had two parallel plates, and that's the positive one, and our field lines for a uniform field are parallel, perpendicular to the plates, and always going from the positive to the negative. Or if we had a plus charge and a minus charge, then our field line does that, and then that. Okay, and then for two like charges, I'll do two negative charges. Our field lines are now going in. Like that. They're all going in because a positive charge would be pulled in along those lines. And then we can start thinking about if we've got a positive charge and a negative charge. Let's start off with two positive charges. Call that Q1. Another positive charge, Q2. That must be a point somewhere in between where the overall field strength is 0, because we colour code it. Make that one blue. So that one's pushing that way. Make that one green. That one's pushing that way. So there must be a point where those two things balance. So I'm going to define two distances. R1, so this point is a distance R1 from Q1 and R2 from Q2. So the two field strengths must be equal. So 1 over 4 pi epsilon naught Q1 over R1 squared equals 1 over 4 pi epsilon naught Q2 over R2 squared. Obviously, we can eliminate the 1 over 4 pi epsilon naughts in no time. And we quite quickly get an equation for the ratio of ratio of the two R's, so R1 over R2 is the same as squared Q1 over Q2. And then that we can square root both sides. So you get R1 over R2 equals the square root of Q1 over Q2. And if you're doing a multiple choice paper, you'll often find, yeah, they've done something really clever, like, you know, Q1 is 27. It'll be milli or micro, but you get the idea. Q2 is 3. So 3 to 1 ratio, square root 9 to 1 ratio. So 27 over 3 equals 9 over 1. But when you square root it, you get a 3 to 1 ratio. So then, if we choose a new colour, don't do that, John. So if we said that distance there between the two charges was 5 metres, how far from the left-hand charge is the the field strength? 0. So we go back to here. We said that Q1 is was 27, or 9 times bigger than Q2. So we're going to be right out over here for our 0 field strength. So we've got to be nearer the smaller charges. So we're dividing 5 metres into 4 parts because it's a 3 to 1 ratio, of which 3 of those parts are R1. Okay, and then obviously R2 you can either do by saying it's one of the 4 parts or just taking it away from the 5 metres. Right, and then we've got to do the same for if we have a plus charge Q1 and a minus charge Q2. We have the same. Now we can say there's a point where the potential is 0 because these are scalars. Positive charge makes a positive potential. The minus charge makes a minus potential. So there's a point where they add up to 0. So let's again put in some kind of crazy simple numbers. We'll also make that 1 and we'll make that minus 2. We'll make that 6 metres. So potentially is 1 over 4 pi epsilon naught Q over R. But I think we can see that the 1 over 4 pi epsilon naughts are going to cancel. So again, we'll divide this up into R1 and R2. So Q1 over R1 is Q2 over R2, which is 1 over R1 equals minus, sorry, if you add them up, it equals 0. So that plus minus 2 over R2 is 0. So what I'm saying here is the potential from the left-hand charge plus the potential of the right-hand charge must equal 0. One of them is negative. So that gives you 1 over R1 equals 2 over R2. So R1 over R2 is equal to a half, or they're in a 2 to 1 ratio. Let me just put the charges back on here. So we've got the left-hand charge Q1 was 1, that's minus 2. So we've divided our 6 metres into 3 parts because it's a 2 to 1 ratio, 1 to 2, of which 1 part is R1 because we've got to be close to that. So it's 6 metres divided into 3 times by 1. So it's 2 metres here and 4 metres here. And then finally, if you've got any energy left, let's think about our accelerating electrons. So we've got a vacuum. We have a filament to boil out some electrons by getting really hot. We have a little tube to accelerate our electrons. We make that positive, we make that negative, and the energy of the electron is EV, because that's the energy per coulomb, times by the coulombs is a half mv squared. So that's how we'd work out how fast our electron would going. And if we then want to steer it, we have two metal plates. The field between the plates is E equals V over D. And then the force on the electron is the field strength times the charge. And then the acceleration is F over M. So that's EQ divided by the mass of the electron. So that's how much our poor old electron, as it comes hurtling along here, if we've made the top plate positive and the bottom plate negative. Right, I've just noticed very naughtily I've now got 2 voltage V's on the screen, so I'm just going to resolve that. So we're going to call that V acceleration, and we're going to call this voltage here that's making our electron acceleration up, we're going to call that V deflection, because I called it V. Okay, so that's yeah, that's that, and so that gives us the acceleration upwards. So it's got, in this direction, it's got constant velocity, so we can work out how long it stays between the plates by doing speed equals distance over time, parallel to the plates. And then perpendicular to the plates, once we've got the acceleration, we can use SUVAT to see how much it's accelerated. Well, that was quite a lot, but probably better to try and hit most of the points. Well done for getting this far.